Okay, so let's get started. Let's assume that you are a simulation model and you work for Amazon. And Jeff Bezos calls you personally because they're going to build a new warehouse. And he says, Ben, I'll give you all the information where the conveyors are going to be. We've got it all planned out, but we need you to verify that it's a good design. Can you please build a digital twin for me? He says, Jeff, no problem. I've got AnyLogic and I know how to use the material handling library. So I'll build you a digital twin, and you go off, do that. You drag and drop things over. You put everything into place. You do your verification, validation of the model. Everything works fine. Everybody is happy. The model is a great representation of reality. And then it's March 2020 and the COVID-19 pandemic hits the globe and Amazon has a lot more workload to do than usual. Jeff Bezos calls you again. He says, Ben, we're going to extend that warehouse. We're going to double its size. Everything is going to be shuffled around. We've got a new layout. The experts have it all worked out. You built that digital twin, right? Can you just put in the new data and let us know how it's going to perform? And it is then that you realize that, maybe I didn't build quite the digital twin, more like a static digital twin, because you would have to go back into the model and rewire everything, rearrange everything, redraw everything from scratch. But Jeff Bezos expects results tomorrow. So what to do? Okay, but before we get started, let me briefly introduce myself. So my name is Ben and I have over 10 years experience in AnyLogic and simulation modeling. I started using AnyLogic in my PhD. And for over 8 years now, I'm working as a industry consultant. So I created models for manufacturing, healthcare, aerospace, defense, even a gold mine in the Andes Mountains. So lots of different things, which is a lot of fun. A couple of years ago, I joined McKinsey to bring simulation modeling to management consulting because I thought that's a loophole. Nobody's using it there, or very rarely. So that was a lot of fun as well. And 2 years ago, I created my own company and now serving the same types of clients, building simulation models day in, day out, which is a lot of fun. Recently, though, I also started doing something a little different with a partner, Goldward Research Labs. We developed a library for AnyLogic, which you can download now, and it helps you create amazing user interfaces for your AnyLogic models. So very easily with drag and drop simply, you can create models that look like modern apps. You have animations, things floating in and out. So that was a lot of fun as well. But let's get back to where we are supposed to be, which is not material design, but we'll talk about material handling library, the library that you get with AnyLogic. Okay, let's get back to our example where Jeff Bezos is calling you and basically saying, I need results tomorrow for the new warehouse. Wouldn't it be nice to simply take the data of the new layout and where everything is and how it works together and let the model self-configure itself instead of you dragging and dropping? It would just be a click of a button. So this is what this webinar is about. Typically, you work with what I call a snapshot of reality. You have a static setup information of where the things in your system are and how they interact. And you kind of hard code that into a model with drag and drop and manual setup. Then you add some live data or flexible data, like how many packets are coming through, what the failure rates are, things like that. Typically you do that and you get something that I would call a static digital twin. So in this webinar, we want to learn how to create a true digital twin, one step further, where the setup information is live data as well, where the machines are, how it all interacts. And you use that to create a model automatically, self-configuring from the data. Then you feed in your live process data as usual, and you have that dynamic twin. And you can rerun that as often as you want with a new configuration setup. Just load the new data. A machine is broken down, just change the data. A new machine is arriving into your facility, just change the data. That's what this is about. Okay, before we discuss what we're going to do in this webinar, let me briefly state that we're going to use the material handling library of AnyLogic, but the principles you're about to learn you can apply to any other model using any other library. So no matter if you build a pedestrian model or just a normal process model, an agent-based model, it doesn't matter. The reason why we chose the material handling library is it's probably a little harder to apply to than the others. There are a couple of smaller caveats that you need to be aware of. So that's why we chose to use this library. If you master this one, you'll master the other ones easily. So let's have a look at what we're planning to do. We're going to build a model that's completely data-driven, and it will include a couple of machines here. Start this. So we'll have machines processing packets, and these packets will be transported between machines using either conveyors or little forklifts. And we're going to split this up into 3 chapters or 3 sections. First, we will create our machines and products programmatically. So we'll have machine agents, put them into a spatial relationship and make them produce products. In chapter 2, we're going to add the conveyors programmatically. Again, from data, these will self-configure to be set up between those machines. And then in chapter 3, we will add those transporter forklifts that can navigate in free space. So what we'll not do is drag and drop conveyors manually, drag and drop transporters manually. We'll do it using a data-driven approach, a self-configuring approach. Okay, so we're almost getting started now. Just one final note on some prerequisites. So this webinar is going to be a little bit more advanced. It's not for the absolute beginner of AnyLogic. So I do expect you to understand simple Java coding, syntax. It would be good if you understand object-oriented principles to a little degree, and also that you just know AnyLogic a little better than just having started yesterday. If that's the case, there are lots of other learning materials out there to get you started, and also just feel free afterwards to reach out to me with any questions that you have. Also, in this final model that I'm showing you here, you see actually I'm using a special UI from that library I mentioned earlier. In the model that we're going to build together, we just use standard AnyLogic components, so it will be completely copyable by you. And then last but not least, in the model itself, I'm using my own little naming convention. Don't get confused by it. I think it's very appropriate to use it. It's very simple that variables have a v underscore in their name. Functions start with f underscore and stuff like that. So don't get confused. Good. So time to get started. Let's start with chapter 1, where we will create 3 machines and products that need to be produced at those machines programmatically from data. Okay, let's find out what we're gonna achieve in this chapter. We're gonna build a model where we have 3 machines that live in 2-dimensional space, but we'll animate them in 3D as well. And what we have is that we'll create product agents in a source object. They will find their first machine. They will have a work plan. They will find their first machine. They will move to individual machines like this one, queue, do some machining, and then either move on to the next machine or just completely exit and finish. And each machine processes these products. And all this will be driven by a database file. So let's start from scratch. Have a new model open, create a new model, and then create a new database. The database that we create will have 5 columns, just a unique ID, a name, position values, and then just another column for the cycle time. So let's fill it with 3 machines, add specific positions, and let's just give them some cycle times. It's just important to note that for our purposes, we'll keep the database tables fairly simple, but obviously you can extend those principles and make this self-configuring model as complex as you like, make those machines as complex as you like, all data-driven. We just define the name and position now. All right, so the next step for us is to create machine agents from this input data. Normally in AnyLogic, you do that directly via populations, but in our case, we'll keep the control and we'll do it manually. So for now, create an empty agent machine and then populate it with a 3D shape, a 3D animation shape, and parameters that match our database table. So I used a pasting machine here. I added my parameters that match my columns. And then on main, you simply create an empty population of that agent type. So I call my populations pop machines. I make sure they're empty. And now we're gonna create our machines manually using a little bit of Java code. The reason for that is normally you can say load it from database and then map your parameters from the database, which is all nice and well. But we need to keep full control over our machine agents, i.e. in which network space and in which level they're going to live. And we'll get to that later. But for now, let's just create them manually. Okay, so I've created a little function fcreate machines, which goes into the database, loops through every entry, and creates our custom machine agent, puts it into that population. And then crucially, I also change the position based on the database. Notice also that I've created another function fInitializeModel, and we'll use that for various steps later on. For now, all this is doing is calling our fcreateMachines function. And in order to actually create the machines on startup of main, let's initialize our model for now. And let's see what happens. So if you run the model now, you see 3 machines have been created. We have the little animations at the positions. And if you go into the individual machines, you see the parameters being filled. So far, so good. The next thing to do is to create a product agent type, a simple normal agent type. The only thing you need to make sure is in the properties to say in a flowchart, this should be a material item, because we're using the material library that will basically turn on lots of characteristics that our products will need. So once you have that, make sure to create another population on main where we're going to track all our products. And that will also be initially empty. And then in the product itself, we're going to add a couple of things. A little animation, like a box. And then more crucially, we're going to have a little collection of machine agents. These are the machines that we want or still need to do as a parcel, as a product. And it's a linked list, so that means it's like a to-do list of machines to do. We're going to add a little vCurrent machine. That is the machine I'm currently at, just to keep track of it. And then machines done, another linked list to track all the machines that the parcel has done already. More importantly, we're going to add a little function create work plan. In this one, very simply, we're going to create our work plan of machines. So we're going to say, I want to visit between 2 and 10 machines. And then for each one of them, we're basically adding a random machine from the list of our machines, from our population of machines. So we're going to fill at the start of the model, we're going to fill our machine collection with our work plan. Now, if you would start the model now, nothing would happen. We still need to create some products, and we do that using the simple process library where we're going to use a source object and create product agent. So let's create a source object, create products with a random rate. We'll create them. Make sure that your new agents are product agents. You can just keep the dimensions for now. And then we also get to add them to this custom population. Then we have an exit block where we say when a product agent arrives here, let's find the next machine. And what we're going to do is we're going to take the first machine from the product's machine to-do list. So basically, where do I need to go next? And then we're going to send that parcel there, and we're going to see how that works in a second. But before that, let's also allow products to finish their life cycle. When they have finished their final machine, we have an enter block that takes them from the machine, and then we just destroy our products in a sync. So how can we link this then, send our products to the next machine? We need to have some process in our next machine as well. So let's do that next. So in our machine agent, we'll have a simple enter block, arrive at the machine, which takes products. Nothing else happening here. We have a queue with maximum capacity where all the products will be queuing. And then we have a simple delay, which assembles or does something to our products at this machine using the cycle time. I keep that 2 seconds for now, actually, because otherwise it gets too busy. And then we need to update the little tracker in our product. So when a product enters, we'll say, I'm now at this machine. And we will also at the same time remove this machine from the to-do list because you're already here. A little sanity check. It's always good practice. And then when we exit this delay block, we'll tick off the machine. So we'll take our current machine and put it into the machines done list. That's all we're doing. And then the next step is we'll check, do I have another machine in my to-do list? If yes, I will go to that machine. So very similar, I find my next machine, which is the first in that to-do list. And then I'll put myself into the arrive machine enter block at that next machine. So basically I'll pop up here again. If I don't have another machine, I just simply exit, go to main and the from final machine, and I end up here and be destroyed. So if you run this model, it should also work seamlessly. So still doesn't look like much, but we can see products are being created roughly every second. They find ways to the machines, and then each individual machine is doing business, and you can see things are either going one way or the other. So hopefully so far this was smooth sailing. This is very standard setup, very standard stuff. Now we're going to start actually creating some spatial layout programmatically. And we're going to start with our little machine, because we're going to have to want a little arrival bay, a little departure bay, a couple of other spatial points around this machine. And we're going to want them to be created programmatically so we can actually use them later on. So let's get started. First of all, unrelated to that, I'm going to add a little rectangle here in the background where if a user clicks on it, he's basically taken directly into this machine. And we'll also display the name of this machine using our parameter. Okay, as the next step, I've now added some spatial objects. I've added a rectangular node, a couple of point nodes around my machine. So we're going to have a queuing area, a leaving area, a machining area where the actual machining is taking place. And then for later on, we also add some points for the conveyor end and start points, but that's going to be in the next chapter. However, if you are careful, you might have noticed I named those things node queuing fake. And also all those elements are invisible. If you run the model, you're not going to see them. They're not going to be part of the model. I'm now starting to do some tricks, and this is one of them. It's not actually possible for you to create some spatial objects using the drag and drop method like we did now, and then at the same time some of them data driven and combine them. That's not possible. As soon as you drag something in, this is like a static network of spatial relations is created for you, and it is finished by the time you start the model, so you can't get into it anymore. So upfront you have to make a decision. Do you want to do everything dynamic or everything static? And obviously we want to do everything dynamic. But I've created those little guys as little fake placeholders. And you're going to see why in a second, because now we're going to start creating our spatial objects programmatically. Let's use a function and a good number of variables. So I've created a function, create space markup. And for every of our space markup guys over there, I've created a variable of type rectangular node for our leaving node, of type point node for our machining nodes. And these are now both visible and not fake. So these are going to be our actual spatial markup elements. And we're going to create them at the start of the model programmatically using this function where we will actually instantiate our node queuing in this example, a point node, a rectangular node. We're going to instantiate it, and then we're going to set its position and size and line color characteristics using our fake equivalent. That's why I use those guys. And this is like a little trick to make your life easier, because some elements you don't actually need to do fully data driven. They are static. These areas don't change for a machine. So you might as well keep them here and be able to play around with them at design time, but still be able to have full control over everything using this kind of code. Now, once we've created those markup elements, the last thing is we need to add them to what's called a network. And you might not be aware of it, but normally when you drag in spatial elements, AnyLogic creates a network for you in the background automatically and adds those guys. That's what I said earlier. This is already done and finished once you start your simulation model. For us, we need to do this manually, and we're going to do it on main, which is where we're going to have our network. So I created a variable of type network, which is going to be the network that we will be using, that we have full control over. And I also created a new function fCreateNetwork, which basically just instantiates our network inside that variable. And what we need to do in our initialize model is we need to call this first. We'll create our network, then we'll create our machines. Now, the next step is, once we've created our machines, we actually want to create that spatial markup for every machine. So I've created another function, fCreateMachine space markups, where I simply loop across every machine and call our new create space markup function for each machine. And this machine space markup, obviously I need to do after I've created our machines. So the order of things here is going to be very important. First we'll create our network, then we create our machine agents, then we create the spatial markup in each machine. And the last thing we need to do is to initialize the level, because that's one of the things that AnyLogic added recently. You can have levels above each other. And again, by default, every spatial element that you drag in is added to the AnyLogic ground level. But again, we need to have full control over everything now. So we need to create our own level as well and add things to that. So very similar, let's create another variable of type level and have another function initialize level, which instantiates a level. We are saying, please show this in 2D and 3D. And then very crucially, add our network, the network that we've created previously, the network in which all our spatial things will live. Add that to the level and only then initialize the level. And after that initialization, everything is basically frozen and you can't change it anymore. So this needs to happen at the start of the model. And then we're going to add it to the actual overall presentation of main. So it's actually going to be visible at the animation. So in initialize level, initialize model, the last step we need to do is to initialize our level. And now one step back, if we go into the machine, into our space markup creation function, once we've created all the elements, the nodes and point nodes, for each one, we're going to have to add each of those to our network on main. We can use the add all function for that. So once we've created the machine agent, we then create the spatial markup for each machine agent. We add it into this network. And then as the last step, we create a level, add the network into the level and initialize. So when you run the model now, you will actually see our little click thing, but also you can see now these spatial markups. And remember, these are now the programmatic markups that you created. You can see network and level are filled. If you go into a machine, you can also see the markup. It's actually below this rectangle now, but it's there. So the last step that we now can do is actually link our process chart with our programmatic spatial markup. So let's do that. And this is now the nicest thing in the process chart, where you specify animation. You can always just say, where should it be? For example, here we're saying agents should arrive in our queuing node. And very importantly, make sure that you now use your programmatic nodes, not the fake ones here. And also very often you need these little checks, because at the very, very start of the model, these might still be null because they're not initialized, but typically that's not a problem. So you're basically saying, if these things exist, if they have been initialized, please animate there. Same for the queue. You can just select an agent location for the queuing, in this case, node queuing, and so on. You can do this for all those elements. And once you've done that, as a last step, you need to also specify or tell your products, once they're being created in that source, where do they actually belong to which level. So on creation of product, we're going to say set the level of that product to be part of our programmatic level on main v level. And lo and behold, if you run the model now, you'll see your parcels actually popping up in our programmatic spatial world. They'll be machined there instantaneously, hence they don't pop up, and then they jump directly to the next machine. So at the moment, everything is just visible in this little rectangle, but it's working, it's alive, and we'll fill it up in the next phase much more. You can also add a 3D animation to see this in 3D space, and we'll do that for the next phase as well. Okay, so that was quite a lot to take in as chapter 1, but there are lots of things that are going to repeat from now on. And it's really important for you to just follow the principles, understand the principles of what's going on, especially the networking and the level stuff and initializing things. So let's have a look at the next chapter. Chapter 2 is going to be exciting because we're going to add the first material handling elements, really, the conveyors. And we're going to make them connect between certain machines so packets can actually use them. Let's get started. Okay, welcome to phase 2. In this phase, let's have a look at what we want to achieve. As you can see, we will build conveyors in this phase, programmatic conveyors, which will take parcels from one machine, move it to another machine. You can also see it in 3D. And these conveyors will be custom agents defined by us. We'll have a conveyor population inside of which you have a little flowchart where conveying is happening using a custom created conveyor that is loaded from a database. So let's get started. First of all, in the model that we have so far, I just added a little 3D window and a little bit of view area navigation so we can more easily navigate around. As you can see in the final model that I've just shown you, you can obviously add as much UI around that as you want. So the very first step for us in this phase is to actually create a database table again that we can load our conveyors from. So it's a very simple table, just 3 columns, a unique ID column, and then I'm specifying for each conveyor that I want to create from which machine is it coming from and to which machine is it moving to. And I'm using the foreign key setup for that, so I can easily, with a drop-down, select the machine ID from our DB machine table. So each of those unique IDs now pops up here. So I want to create 2 conveyors programmatically, one going from machine 0 to machine 1, and one going from machine 1 to machine 2. Not more for now. All right, as a next step, let's create a new empty agent type myConveyor. This will be the agent holding each individual conveyor. And let's duplicate the database setup with a parameter setup. So we have an int ID parameter and then 2 parameters, machine origin and destination of type machine actually. So we're going to map this integer number to actual machines in a second. And let's create another population on main, our pop conveyors. And as before, let's make that a population of agents initially empty. Let's not load any parameters yet. We'll do that manually. All right, as you can see, we're picking up speed now because lots of things are starting to duplicate. So I create a new function, create my conveyors. And in it, I loop through my database table. And for each row, I now pull out all the individual data, the ID, and now I'm also pulling the machine origin ID and translate it into the actual machine from pop machines. So it's just a little trick here. And then finally, when I have my actual origin machine, my actual destination machine, I actually create the myConveyor agent and map those 3 parameters that we've created previously. Now, obviously, we need to call this function together with the other functions that we've created. And it's very important, again, the order of initializing our model and calling these functions. So before we initialize any level, which is always the final step, we create our conveyors now. If we start our model, we have a lovely filled population of conveyors now, conveyor agents, each with those individual parameters filled. And the machine parameters are actual machines now. All right, so let's actually create a conveyor now. So typically what you do is you drag a conveyor object in here and start drawing it and adjusting shapes. Normally you would do that on main. Things would snap together. You would create a conveyor network. We cannot do that here. We want to have it data driven. So we use the same trick as before. We create a variable inside my conveyor, which is the actual conveyor path. So this is this actual guy here, but initially it's just going to be empty. And on startup of that agent creation, we will actually fill this with the function fCreateConveyor, which creates the actual conveyor. And now we get into a little bit of Java here, where first of all, we create a new conveyor path. Then we do all sorts of things to it. Then it gets even more complex with something called markup segment lines. But let's pick it apart. And a really useful way to understand what's going on here is to actually use the AnyLogic help. If you open the help and search for conveyor, you will eventually come across an entry that has this AnyLogic 8 engine API addendum. And that's always very useful for creating data-driven stuff. So this API basically tells you what this object is and then how to construct it. So if you don't know yet, I strongly suggest you get used to this standard Java documentation and how to read it. But here we can see how we can construct a conveyor path with just an empty constructor in this case. And then we also have a list of all the methods that we can do with this conveyor. So this is what we're doing. We're creating a new conveyor path, and then we're setting all sorts of characteristics for it, which is nothing else as what you do when you drag in this guy and set the characteristics yourself, like the width, the initial speed, stuff like that. So in our case, we say this conveyor should belong to this agent. It should be an obstacle for free space navigation, so later on our transporters don't crash into it. We set the width and speed, what type of conveyor it is, and so on. And then as a last step, we also say, well, where should it be positioned in space? So a normal conveyor can have lots of little subsegments. If you double click, you can have all those subsegments that make up the entire conveyor. Programmatically, you can do the same. In our case, we're going to say create a markup segment line that makes up our conveyor, and it should only be one markup segment line. Again, if you go into the help, read up on markup segment lines, you can see how it is constructed, in this case with 6 arguments that are unfortunately not well documented. But what this means is the X position of the starting point, the Y position of the starting point, the Z position, and then the same 3 things for the endpoints. So in our case, we create a new markup segment line that starts where our origin machine conveyor starting node is. So the X position of that machine. So if you remember, inside machine, we had those node queuing, node machining, and then also the conveyor start, conveyor end nodes, which are these guys here. So conveyors basically conveyors start here and end here relative to individual machines. So now we are saying, dear conveyor, please start at the origin machine and end at the destination machine. So programmatically, we now force conveyors to be between those 2 machines. And then as a last step, we basically say, take all the segments that we've created in this array of segments and add it to our V conveyor. So once we've created this function back in main where we create the my conveyor agents, all we need to do is basically say, for the conveyor agent we've just created, please call that function. Now, if you start your model and navigate into an individual conveyor agent, you'll now see the V conveyor is filled, is active, and is an actual conveyor. Not much more to see for now. Okay, so similar to what we did before with our space markups, when you combine them, they automatically create a network. With conveyors, it's the same. If you drag and drop several conveyors and make them snap together, AnyLogic not only creates the conveyors, actually it creates a conveyor network as well, and all conveyors must belong to a conveyor network. So we do the same programmatically. So let's create a new variable on main of type conveyor network, keep it empty for now. And then when we create our conveyor agents, once we've done all of that, we fill our V conveyor network. So we create a new conveyor network, say it should belong to this main, give it a name, and then we loop through each of our conveyor agents. We have previously created the V conveyor inside that my conveyor agent. So now we're manually adding it to our conveyor network. And then we just make sure that we add that to the presentation as well. That's to ensure that the conveyors are actually shown properly. And then as one last step, when we initialize the level, remember previously we added the network, the spatial network, to the level. Now we do exactly the same thing with the conveyor network before initializing it. So that makes sure that our spatial network is added, our conveyor network is added, and then we have our custom level. Now, if you run your model now, actually you see the conveyors already. One between machine 0 and machine 1, one between machine 1 and machine 2. And they're also there in 3D. But if you look, nothing is actually happening functionally. Our parcels are still jumping between machines. And I hope it's obvious why that is, because in the conveyor agents themselves, there's actually no flowchart that tells products what to do. So let's build a simple flowchart for our conveyors where we say parcels enter through an enter block arriving at the conveyor. Then we queue them as usual, as a good setup with a maximum capacity. Make sure on the enter block you actually set that the agent type is a product. And then now we use a conveyor block. That's where the magic is happening. The actual conveying is being done. So in this setup now, we can actually say with a drop-down list, there's nothing to see. Also with that selector box, there's nothing to see, but we can switch to the dynamic mode and say the source conveyor should be our conveyor, our V conveyor, and same as for the target conveyor. So as soon as a product arrives in this convey block, we say, please take whatever conveyor we've defined here, which we've defined here. So obviously you need to make sure that this function is called before the first product arrives at this conveyor, otherwise it will throw an error. But in our case, that's always the case because we call that on startup of the model. Now, once we've done the actual conveying, obviously you can make this more complex if you want to. We'll have another check similar to what we had before, where the product should go next. If it has another machine, it should just then arrive at another machine at its enter block. Otherwise, we just send it to the final machine block on main to be destroyed. Now, with this setup, we still are not actually sending any products here. We need to do that in our machine process flowchart. And we're going to change it slightly, as you can see here. So after we've done some machining, first we check if there is another machine as before. And then we check, is there actually a conveyor from this machine where the product just finished to the machine where the product wants to go. So for that, I'm basically calling another Boolean function has correct conveyor, give it this product. And in this function, I'm now using a little, well, it's not a trick. I'm basically checking something. So first of all, I create an agent link on my machine, the connection to the conveyor, to the my conveyor. It's going to be just a single link and I'll make it bidirectional. So I'm saying in my conveyor, please create a similar connection con my machine. And when you click OK, that will, I've already done that. So in your machine, that will create, so in your machine, this will create a similar connection, my machine. So this is now in my conveyor, it has created that element. So now a conveyor knows about its machine that it's linked to, and a machine knows about a conveyor that it's linked to. And the default definition is that a machine is linked to its downstream conveyor. That's how we're going to interpret that. So now in our function, do we have the correct conveyor? We are checking, do I have a downstream conveyor being the machine? Then I find out for the product that's now coming, is there a downstream machine? And does that downstream machine also have this? So I'm returning true here if there is a conveyor between this machine and the machine that the product wants to go to. So if this returns true, we basically now send our product into the downstream conveyor. So we go into this machine's conveyor and push the product into the arrive at conveyor. And this will make it move along the conveyor to the next machine of that product. So once it arrives, remember it just goes into its list and is then starting the machining at the next downstream machine. If there's no conveyor actually found, that might also be happening based on your data setup, we simply, as before, just beam the product to the next machine. Now, as the last step, when we create the myConveyor agent on main, while we do that, after we've created it, we also need to actually make the connection from the conveyor that we've created to the origin machine where the conveyor originates from. Now, if you run your model now, you will see we have our conveyors moving. We have parcels moving along the conveyor from machine 0 to machine 1, from machine 1 to machine 2, but there are still also parcels going between the other possible path, and these are being beamed. So you can also watch it in 3D. If you look into the machines, you will see some of them find a conveyor, some of them do not find a conveyor. And if we look into the conveyor agent itself, you see the flowchart, you'll see what's being conveyed at the moment and where things are moving to next. Now you can play a little bit more. If you want to, you can animate other things in the myConveyor like the queue. And you could say that this should be animated at the actual origin machine. So here, now I'm basically saying, if the conveyor is full, products have to queue ahead of it. Where do I want to animate that? And I'm saying, well, if you do have a machine, which should normally be the case, go into that machine and use the conveyor start node. So just in front of where the conveyor starts, we just drop everything and animate it there. And you can do that for the other blocks as well in a similar fashion. Okay, so let's summarize. We've created a database table where we specified our conveyors from where to where they should be going. We have an empty population on main. We fill it with a function to create those conveyors, loop across the database table, add our myConveyor agents, fill the parameters, and then crucially, inside that myConveyor agent, we have the actual conveyor itself. We created at the start of the creation of the agent, we set all the characteristics, we set the spatial objects. You could have more markup segments here if you wanted to. And then you just need to be careful on main that you create a conveyor network as well. After you've created all the conveyors, add the actual conveyors to it. And then as a very last step, add the conveyor network to the level that you're creating. Initialize that and you're good to go. And then obviously, as before, use local flowcharts with enter and exit blocks. Okay, that was chapter 2. We've added conveyors. Now it's time to go into the last chapter to add free space transporters as well. So whenever a packet cannot be picked up or transported by a conveyor, we'll now ask a transporter to do that for us. Again, data-driven. Let's have a look. Okay, so in this phase, let's have a look first at what we want to achieve. This time we're going to build some free space transporters. They're going to have a home location and they're going to pick up the parcels that cannot be transported by the conveyors that we've set up. So they basically pick up everything else and move it to where it needs to go. Again, it's going to be data-driven, so we're going to have a database table that specifies them, and then we're going to create them using code. So let's get started. All right, so let's have a look. The thing that we're going to build eventually is going to be the transporter fleet element that specifies transporters. And one thing that it needs for the transporters is a home location. So let's create a home location programmatically first. And we're going to use the same trick that we've used before, where we're going to use a fake rectangle that's going to specify an actual rectangular node for our network. One thing in this chapter is we're going to speed things up because some things are very similar to what we've done before, so don't get confused. So I've created a transporter fake node, invisible. We're not going to use it. We only want its dimensions. We're also going to create a new empty variable node transporters. It's going to be a rectangular node, and this is going to be using the coordinates of this guy. The way to do that is, as previously, I created a new function, create transporters home node. And here I actually fill my node transporters with the position and size of this fake rectangle. And then I add it to our network. So now remember, the network must be initialized before we finish with the level. So now ordering again becomes important. In our main function initialize model, we're going to call the fCreate transporter home node before we initialize the level. So we're going to do that here. So first we create our node, add it to the network inside that function, and then as a last step in fInitialize level, we add the network to the level and initialize that. All right, the next step as before, a new database table, this time for transporters. Similar setup as before. We're going to set up a fleet of transporters, and each row is going to be one fleet. So in this row, we say we want 3 transporters as part of that fleet that are able to serve packets going from machine 0 to machine 2. In this fleet, we want 2 that serve machine 0 exclusively if a parcel needs to go from machine 0 back to machine 0. So it would be transported from this node back to this node by a transporter, and so on. You can make it as complex as you like. So let's start creating agents. First, we're going to create an agent called my transporter fleet, and each instance of that agent will represent one row from our table. And you can just leave that as a normal agent. We will not turn this into a transporter agent yet. We'll do that later. As before, let's create an empty population for this transporter fleet on main. Pop my transporter fleet. Let's make sure it's a population and initially empty. So again, we'll load it with data. And then in the agent type itself, make sure you have parameters that reflect the database table. As before, the machine parameters should be of type machine. Let's add a new function to create transporter fleets. And as before, we will loop through the database table, adjust the parameters, find the right machine agents, and then simply create individual transporter fleet agents in that population. And we will call this function now after we've initialized the level. And the reason for that is that the agent itself is not going to be a transporter, and it needs to live inside the level, inside the network. It needs to be part of it. So it needs to be created after the level has been initialized. Remember, with the conveyors, we link them using an agent link to the machine. We'll do the same with a transporter fleet. So I've created a con my machine, which links to a single machine, and it's bidirectional. So inside the machine class, you will get a con transporter fleet. So each machine knows about its conveyor downstream and its transporter fleet that can take stuff away from this machine. We will establish the connection when we create the transporter fleet. So in the fCreate transporter fleet, after we've created the actual agent, we go into the agent and connect its connection to the origin machine. So again, the assumption is that a transporter fleet always belongs to where it starts serving packets from. If you run your model now, you see we have our population of transporter fleets populated. Nothing else is happening yet with those because there's no behavior specified. But if you go into them, you see the parameters being populated and it's connected to an individual machine. All right, so let's actually start implementing some behavior. In the transporter fleet, we'll add a super simple flowchart where packets can arrive at the transporter fleet. We will animate them at the leaving node of a machine because they're about to be transported away. And then we have the same setup as before where the packets afterwards are basically being beamed to the next machine or to the exit location. So at the moment, it is still lacking actual transport behavior, but we can now make packets move through those agents. Now, the way to actually push them into the transporter fleet is we're going to amend the flowchart in the machine. So once a packet comes through, it checks first if there's a conveyor, so it prioritizes those. But if there's no conveyor, we then check, well, is there maybe a transporter fleet at this machine that could take it? So in this case, we're simply checking if there is a connection to a transporter fleet. And if so, we transfer the packet to that transporter fleet arrival port. So it then arrives here and is doing whatever it's supposed to do. Now notice this time we are not doing an advanced check here if the transporter fleet can actually take the packet to the destination machine like we've done for conveyors. You can do that yourself. It's a nice little exercise to duplicate that for transporters as well. If you run your model now and you go into a transporter fleet agent, you will actually see packets coming through, not really doing anything yet, but at least visiting the transporter fleet and then being beamed to the next machine. So now we're almost ready to implement some actual transporting here. So let's create a transporter now. Remember, this my transporter fleet agent is not going to be the transporters itself. Each fleet agent has several transporters. So we'll create a transporter type, agent type from the material handling library. We'll call it forklift in this case, and then just go ahead and create it. And then make sure you add a little forklift 3D animation so we can actually see the guy. Also then just double check in the properties of the forklift that it does indeed say use in flowchart as transporters. This is crucial to tell AnyLogic this is supposed to be a transporter with collision avoidance and that kind of self-awareness. Then create, as before, an empty population of forklifts in your transporter fleet. So each transporter fleet will have a population of forklifts according to this quantity, but make it initially empty and make sure that you click this show presentation button if it's clickable, and make sure you see the presentation in your transporter fleet so everything will be visible eventually. Okay, so now is the time to actually start dragging in the transporter fleet element from the material handling library and set it up properly. So the capacity, well, first of all, let's say these transporters are going to be free space. They can just drive anywhere. The capacity we can now easily define by the quantity parameter from the database. And then crucially, the home location must be a rectangle or rectangular node that is part of our global network and part of our global level. So that's why we created this rectangular home location up front, because now we're going to tell all the forklifts where you're living is in that rectangle. So you have to dynamically navigate to main and take the node transporters, not the fake one, but the one that we created programmatically. And this needs squiggly brackets because you could actually specify several home locations as a comma separated list. The rest we can leave. All we need to do now is to say whatever transporter agents you create, please create forklift agent types. And then please also add them to this prepared custom population forklifts so we can actually visit and have a look at those guys. If you run the model now, you will see forklifts also in 3D. They should be there. If you can't see them in 3D, go to your forklift agent, click on the animation object and make sure it's clicked to be shown in 2D and 3D. So here we are. And if you then go into the transporter fleet agent, you can see 3 forklifts for this fleet in the transporter fleet and also in the population. Obviously not doing anything yet. So after all this preparation work, we can now finally say, please, if a parcel arrives in the transporter fleet, move it by a transporter, use the fleet that we've just created, the transporter fleet. And the question now is, where should it be going? So first of all, make sure when you send packets into this enter blocks that AnyLogic actually knows what's arriving here are product agents or packet agents. And then in the next step, we can say the transporter should take the packet agent and move it to whatever packet agent is arriving. That's the agent keyword. We go into its outstanding machines to do. We get the first one where it needs to go next. And we get that machine's node queuing, not the fake one, but the actual one for queuing. So the transporter will now drive the packet to its next machine's queuing node. And that's all there is to it. Now our transporters actually pick up packets and move them to where they're supposed to be. And basically relieve the conveyors and do the jobs they're supposed to do. If you go into the transporter fleet, you will now see transporters actually being busy and doing the job they're supposed to do. So let's summarize again. We created a new database table that specifies our transporter fleets. We created those, and then crucially inside of them, we created the actual transporter fleet with transporter agents, in this case forklifts. We use the move by transporter to use that fleet, move it to wherever the packet needs to go next. And one of the critical things and kind of tricks that you need to do is you need to create a home location for your transporter fleet that is part of the programmatic network. Hence, the very first thing we did before initializing the network and level was to create that node transporters, adding it to the network, then initializing the level with that network, and as a last step, create the transporter fleet and set everything up. So that was that chapter. Now you have a functioning self-configuring model with conveyors and transporter fleet. All right, you've done it. We've added free space transporters as well, hopefully giving you all the principles that you need to create other material handling elements or elements from other libraries even. So let's now open up to questions. You were able to ask any questions, and we're going to use the remaining minutes to answer the best questions. In terms of next steps, what I recommend you do is simply try this yourself. We'll send out a recorded version of this, obviously. It'll also be available on YouTube, so you can pause and try to follow the steps. It was fairly fast paced, but there was a lot to cover. And then just extend those principles to what you need to get done. And if you want to reach out to me, there are lots of places you can do that via my website. There's a YouTube channel that I'm filling with little nugget videos. I'm on Twitter, LinkedIn, Stack Overflow, so you can find me in lots of places. All right, let's get to the questions.